Now let's take a look at carbon dioxide. 4 plus 6 times 2. That adds up to 16 electrons, 8 lines. We'll put carbon in the middle since oxygens generally won't bond to each other in a compound. And perhaps we've used 2, 3, 4, 5, 6, 7, 8. And if we do this, you'll notice that this oxygen on the end is 2 bonds away from, or 2 pairs of electrons away from an octet. Let's finish that in a minute, but perhaps instead maybe you started this way and your sense of symmetry said 2, 3, 4, 5, 6, 7, 8. And now you can see that neither oxygen on the outside has an octet. You may also have put this unshared pair here and this unshared pair there, and then your carbon in the middle would not have enough electrons around it. This means we need to do multiple bonds. So I will erase those 2 unshared pairs and end up with double bonds in the middle. Or I could do something different. Perhaps on this side you'd say, well, let's move those and put a triple bond in between the carbon and the oxygen. Octet for the oxygen, octet for the carbon, and certainly for this oxygen, just as each oxygen over here with an octet and the carbon in the middle. Is one electron arrangement better than another? Well, yes, scientists have been able to do infrared studies and determine if a single and a triple or 2 doubles is what actually happens. And as a result of these studies, scientists have said, do we have a way we could predict this, looking at these 2 structures? And so let's introduce what's known as formal charge. This is not actually real charge, but a bookkeeping system or a prediction method. And so we use this to assess what's known as resonance structures. This is different from isomers. Same atom arrangement, well, same chemical formula, certainly CO2. Same atom arrangement, but different electron arrangement. In other words, we're not shifting which atom is bonded to which, but we're shifting electrons around. And so we have this tool called formal charge, which will allow us to predict which chemical formula might be better than the other. Here's how we'll get this done. We'll need to consider each atom in both formulas separately, one at a time, by looking at the number of valence electrons the atom has, subtracting the number of non-bonded electrons around that atom, and lastly considering the number of bonds. So let's do that in the first structure. The oxygen has 6 valence electrons. Notice that there are 1, 2, 3, which is 2, 4, and 6 electrons. So let's subtract 6, and let's subtract 1 to end up with a -1 value around the oxygen. The carbon in the middle. Carbon has 4 valence electrons in the periodic table. There are no unshared pairs on that carbon, and there are 4 bonds. As a result, we'll have a formal charge of 0. And lastly, the oxygen on the right-hand end with 6 valence electrons in the periodic table, minus 2 for the unshared pair, minus 3 for the 3 bonds, 1, 2, 3, and we'll end up with +1. So we do have some formal charge. Now we would like to compare that with the formal charge on the other side. And so both oxygens are the same, meaning 6 minus 4 for the 2, 4, the unshared pairs, minus 2 for the 2 bonds, or the 2 bonds here, and both oxygens come out the same with a value of 0, so we can put 0. The carbon in the middle, carbon has 4 valence electrons, there are no unshared pairs, minus 4, lo and behold, we'll end up with a value of 0. After calculating the formal charge for 2 different structures, the structure with the least amount of formal charge is going to be the preferred structure. And so we'll get the red pen and put the big circle around the structure on the right, 2 double bonds. Let's add the valence electrons. 5 times 2 plus 6, 16 electrons. So let's put the nitrogen as suggested in the middle, so a nitrogen attached to another nitrogen attached to an oxygen. 3, 4, 5, 6, 7, 8. We'll need to do some backtracking and shift some electrons to end up with 2 double bonds so that all the octets can be satisfied. We might be able to rearrange the electrons and end up with 2, 3, 4, 5, 6, 7, maybe 8 here, and lo and behold, of course, we are going to need multiple bonds, so we'll shift the electrons and put a double here, erase and shift again, and maybe turn that into a triple. Now that triple could just as easily have been on this side between the 2 nitrogens, so let's represent that. Nitrogen, triple bond, single bond to the oxygen, complete the unshared pairs. Now what we'd like to do is say, out of these 3 possible structures, let's use formal charge to predict which structure is most likely. Formal charge would be 5 minus 2 minus 3 bonds. We'd get a value of 0 for this nitrogen. The nitrogen in the middle would be 5 minus 0, no unshared pairs, minus 4. That'll give us a positive 1. And the oxygen on the right with 6 valence electrons, minus 6, 2, 4, 6 unshared electrons are non-bonded electrons, minus 1 will give us a value of negative 1. And so we do have formal charge here. Let's check the one in the middle. 5 minus 4 minus 2. We'll end up with a negative 1. And the nitrogen in the middle, 5 minus 0 minus 4 bonds, positive 1. And the oxygen on the end, 6 minus 4 minus 2 equal 0. And so we have formal charge here as well. Formal charge will always add up to 0. The compound is neutral, so even though this is just a predicting tool, the formal charge, a check that you can do is to be sure that any formal charge that does end up on a molecule will add up to 0. And let's check this last compound, or last electron arrangement. 5 minus 6 minus 1, negative 2. And the nitrogen in the middle, 5 minus 0 minus 4, positive 1. And the oxygen on the end, 6 minus 2 non-bonded electrons, minus 3, to end up with a positive 1. Again, the formal charge will add up to 0, but we were looking for the least amount of formal charge. That means we can cross this off, and then we're left to decide between these. If we end up with two sets of formal charge that's the same, a positive one and a negative one, we want the negative formal charge to end up on the more electronegative atom. That would be oxygen, and so that makes this structure preferred. So we'll preferred structure, and lo and behold, experimental evidence has supported that there'd be a triple bond between the nitrogens and a single to the oxygen. Now, why didn't we put oxygen in the middle? Let's just take a quick look at one of those options. Would be nitrogen, oxygen, nitrogen, and you could choose the double bonded one with the two unshared pairs, and if you check your formal charge, we will end up with five for the nitrogen minus 4 minus 2 will give us a value of -1, and the oxygen in the center will be 6 minus 0 minus 4 will give us a value of +2, and the nitrogen on the end will be the same as the other, also a -1, and so we've got more formal charge than we have here, and so not. And the same if we had put a triple bond, we would again see more formal charge if you had ended up with structure that looked with a triple bond. The formal charge will also be worse than the formal charge over here. So these isomers do not exist. N2O will indeed be this structure.